Greetings and welcome to this dynamics analysis of the Albatross UAV, featured as a part of our flight dynamics course laboratory. My name is Nahyan Al-Lahiri, and throughout this video I will be providing a flight test briefing for the Albatross UAV, using Unity simulations to guide you through the process. First, let's discuss the weight and balance aspects of our aircraft. The aircraft center of gravity, or CG, is represented by this black and white sphere, while the mean aerodynamic chord is represented by this blue line. The front of this line is positioned at the coordinates x0, y0, z0, and the CG longitudinal axis corresponds to the z-axis. As we shift the CG along this axis, or let's say in front of the mean aerodynamic chord, it becomes more negative, and if you shift it back, it becomes more positive. Now we will load the weight and balance data for our aircraft. The aircraft is displayed resting on three weighing scales, each indicating the mass reaction on that particular scale. By knowing the distance between the wheel relative to the aircraft and the forces acting on them, we can compute the moment on each wheel, which allows us to get the CG's location. Also, adjusting the Z value of the CG, we can observe the changes on the locations of the CG and the reactions on each force balance. We can experiment with different CG locations within Unity, calculating the measured load on each point by inputting this data, along with the wheel locations into Excel. We can calculate the moments and determine an estimated CG location, as we already know the weight of our aircraft. We can then compare this data to our actual CG values to ensure their accuracy through this graph. Also, through the experiment, we found the unstable CG locations, which, as you can see, will cause our aircraft to flip backwards or uh, forwards, depending on what's set to change. Next, let's examine the thrust test setup. At the front of the aircraft, a load cell measures the thrust produced by the aircraft. We will determine the static thrust when the CG is at 25% of the mean aerodynamic chord, and the RPM will be displayed on the top corner. We will start taking the RPM to 100%, and we will find that the maximum load will be 28 newtons. After gathering data for various points and entering them into Excel, we can create a plot of the static thrust for each RPM, and this will provide the pilot with an understanding of the static thrust at different points during calibration. Following that, a static control response test was performed. During this process, it's important to fix any controls that aren't functioning correctly. Once these issues are addressed, the test confirms that the appropriate inputs from the pilot results in the correct corresponding outputs from the control surfaces. Subsequently, the evaluation of the aircraft's longitudinal dynamics was conducted by taking into account the influence of wind velocity and CG location on pitch movement. The study began by examining the aircraft's pitch reaction to elevator deflections under different frontal wind speeds. These particular graphs confirm that when the elevator deflections are modified, a corresponding shift in the aircraft's angle of attack occurs, and that the graphs highlight the impact of rising wind speeds on the aircraft's longitudinal stability. As seen in this graph, the response to a large elevator deflection, the angle of attack's fluctuating amplitude decreases, while the decay time is shortened in response to increasing wind speeds. The analysis continued with a test of the aircraft's reaction to adjustments in the center of gravity relating to longitudinal instability. The following charts revealed how changes in the vertical aspect of this CG influenced the aircraft's longitudinal behavior. When the CG moved more toward the rear, the aircraft displayed high sensitivity to elevator deflections, leading to a reduction in static margin, causing more significant angle of attack variations. Following a control action that shifted the CG in a forward direction, both the amplitude of oscillating and the time required for the angle of attack to dissipate increased. When the aircraft pitched upward, it tended to roll to the left, causing considerable angle of attack oscillations as shown in the graph. These oscillations continued until the center of gravity position reached 35% of the mean aerodynamic chord. Consequently, when the CG was forward, the aircraft exhibited an insufficient response to deflected elevators. Upon analyzing the data in Excel from the lateral response test, it becomes evident how the free stream velocity influences the roll rate. Higher velocities results in increased roll rates. When comparing the yaw response, it can be observed that the dampening of the yaw response is significantly lower than the roll response. Next up, we conducted the wind tunnel test to see how the aerodynamics coefficient change with different center of gravity positions, flap deflections, and elevator deflections. As we increased the flap deflection, the lift coefficient went up as well. The highest lift coefficient we got was around 1.2 with a 40 degrees flap deflection, and we found the stall angle of attack to be around 15 degrees. All of these results were from the wind tunnel test at a speed of 10 meters per second. Before going into free flight, we use a center of gravity position within the suggested range and perform a ground maneuvering and taxi test. The goal of this test was to make sure the pilot had enough control when handling the aircraft on the ground while taxiing. So the minimum speed required to fly the wheels off the ground without flaps is approximately 27 meters per second, as you can see. And with the flaps deployed, the speed decreases to about 25 meters per second. Notably, this is a significant higher number than the estimated stall speed by around a factor of 3. During this test, the goal was to trim the aircraft at around 20 meters per second, as shown. The Albatross flew at 25 rpm with an elevation trim angle of negative 5.87. Also, the maximum speed the aircraft attained while maintaining trim was approximately 50 meters per second, as demonstrated in the video. Next, the fugode motion of the aircraft was examined. This refers to the long period oscillation of an aircraft at a constant angle of attack, which typically leads to an uncontrollable spin. Finally, after achieving a trimmed and stable aircraft, we managed to free flight around the test course, aiming to maintain a speed of 20 meters per second at a target altitude of 30 meters. Thank you.